You are given an undirected tree with n nodes labeled 0 through n-1, connected by n-1 edges. Choose any node as the root. The tree height is the maximum number of edges on a path from that root down to a leaf. Find every root label that gives the smallest possible height. Example 1, for nodes form a star centered at 1. Root at 1 puts every leaf one edge away, so the height is 1. No other root is lower, so the answer is the single label 1. Example 2, 6 nodes. After stripping outer leaves, nodes 3 and 4 remain in the middle. Either one as root gives height 2, and nothing else ties that minimum. Output is 3 and 4. If we blindly select an outermost node on the edge of our graph to act as the root, the tree stretches out into a tall, unbalanced structure. This creates a massive distance to the furthest leaves, maximizing our tree's overall height. To minimize the tree's height, we must find the absolute structural center of the network. Positioning our root at this central core pulls all outer branches inward, distributing the nodes evenly and minimizing the distance to the furthest leaf. We can pinpoint this center by working from the outside in. We identify all current leaf nodes, the vertices with only one connection, and trim them off the graph simultaneously, peeling away the outermost layer of the network. We repeat this trimming process level by level, continually isolating the new outer leaves and snapping them away. Because a graph can have at most 2 center points before collapsing, the final node standing when the peeling stops are our definitive minimum height tree roots. We begin by mapping out the topology of our network. We construct an adjacency list to track connections, while simultaneously maintaining a degree array that logs exactly how many edges are anchored to every individual node. With our graph fully mapped, we sweep our degree array to isolate our initial base case. Every node displaying a degree of exactly 1 represents an outermost leaf, which we immediately collect and inject into our processing queue. To peel our network from the outside in, we run a coordinated loop that continues as long as there are more than 2 nodes remaining. We snap a snapshot of our current queue size to ensure we process our leaf layer completely in a single unified step. As each leaf is popped, we sever its connection to the rest of the graph by decrementing its neighbor's edge count. If cutting that edge drops a neighbor's remaining degree down to 1, it has officially become a new outer leaf, and we immediately queue it up for the next layer of trimming. When our loop conditions terminate, the peeling process stops completely. The final 1 or 2 nodes trapped inside our queue represent the absolute core centroids of our original network, returning them as our optimal minimum height tree roots. Let n be the number of nodes in the tree. Time is O of n, each node is peeled at most once, and each edge is touched only when a leaf neighbor drops off. Space is O of n for the adjacency lists, degree counts, and the leaf queue. Main routine, minimum height tree roots by leaf peeling. Tiny trees return every label directly. Prepare one neighbor list per node. Track how many edges touch each node. Walk every undirected edge once. Record V as a neighbor of U. Record U as a neighbor of V. Bump the degree count at U. Bump the degree count at V. Start the processing queue empty. Scan every node label. Enqueue each current leaf with degree 1. Count how many nodes are still in play. Peel while more than 2 nodes remain. Snapshot the current leaf layer size. Drop that many nodes from the remaining total. Process every leaf in this layer. Remove the next leaf from the queue front. Visit each still connected neighbor. Cut one edge by lowering the neighbor degree. If the neighbor becomes a new leaf, and queue it. Return the one or two centroids left in the queue.